Hello everyone. In this session, we'll be solving some problems related to Pythagorean theorem and its applications. So we'll be covering two problems in this session, and I'll give one of the problems as a homework to you so that you could try out and see if you can get some progress on that problem. So let's begin with this first problem, that is from the Russian mathematics Olympiad from 1955. So it says that find with proof all integer solutions to x cubed plus 2y cubed equals to 4z cubed. So you can pause the video and try this problem, and when you are done you can watch the solution. So let's begin with the proof to this problem. So what we can do is we can rewrite this equation as x cubed equals to 4z cubed minus 2y cubed, and then we can take a common factor of 2 from the right hand side, so we get 2 times 2z cubed minus y cubed. So for this thing, that is, the right hand side is a multiple of 2, so we can say that the left hand side has also the left hand side must be a multiple of 2 as well. So we can take x equals to be some 2k and then rewrite this equation again, so we'll get 8k cubed, or rather we can take x to be 2x prime. So we get x equals to 2x prime, and then we can rewrite this equation as 8x prime cubed plus 2y cubed equals to 4z cubed. And then we can take a common factor of 2 from both the sides and then cancel it. So we get um, 4x prime cube plus y cube equals 2z cube, and then we can send this to the right hand side. So sending this to the right hand side, and then again we rewrite the equation as y cube equals to 2 times z cube minus 2x prime, and this is cube. So we say that y also must be a multiple of 2, so we can take y equals to 2y prime, as y must be a multiple of 2. We can see that here we have a factor of 2, this thing, so it must be a multiple of 2. And then we can again rewrite this equation as so we again rewrite this equation as 8x cubed plus, so let me fix that. So 8x cubed plus 16y cubed y prime cube equals to 4z cube, and then we can take a factor of 4 common from both the sides. I think, let me see that if that's right. So yeah, that's right. So we get 2x prime cube plus 4y prime cube equals to z cube, and then we see that z must be a multiple of 2 as well, so this has to be 2x prime cube plus 2y prime cube equals z cube, hence z must be a multiple of 2 as well. and then we can make a claim that so what we see is that if we try to make a claim that if the original solution that we had in the earlier, that is this one, this thing, so this x cube plus 2y cube equals to 4z cube, and if this has a solution, that must be a primitive one. So we can take that as a so we can take the GCD of some solution, some primitive solution, to be 1, and if that doesn't happen, so that's a contradiction to our assumption, and hence we'll have no solution to that. Let's see how we can do that. So our claim is um okay, so this thing, so our claim is, let me rewrite this. So our claim is that we have okay, so our claim is that we have a solution that is primitive. So we can claim that we have a solution that has GCD1, like the solution XYZ must have the GCD to be 1. So that has XYZ equals to 1, and this is the GCD. Now let's see if that doesn't happen, we'll say that our assumption was wrong and we have a contradiction. And from here we can say that, okay, so from here we can say that since x, y, z have a common factor of 2, and that process goes on forever, like you see a infinite distance between that, so we can say that our claim was wrong, and all of the three numbers must have a common factor of 2 in them, like they all extend and have a common like infinite distance thing. So you can say that we have a contradiction, and the only solution we can get um, is 0 comma 0 comma 0. Like this was one of the things which doesn't have any common factor. Like you can see from here, this is one of the trivial solutions. So you have this thing, so you put 0 comma 0 comma 0 and you find the value. So that was one of the trivial solutions, and you don't have any other solutions apart from it. So we can write our key takeaway from this thing. So let me write that. So the takeaway, I mean like the key point. So the key point was, so we can say that if we have a homogeneous expression, if we have a homogeneous expression for example with variables, xyz, then we will have, okay, let me rewrite that. Then we will have infinite solutions of the form kx, ky, kz, where k can be the GCD of xyz. So if you see that, if you have a homogeneous expression and you have this common factor as k, and you have the common factor as k, so this will always cancel out each other, and you'll always end up finding the one of the solutions that is scaled up by some factor k. Now let's see the next problem. So let me write the problem, and that is from the 1977 IMO. So the question is from the IMO 1977, and this was problem number 6, and it says that find all the functions that goes function f that goes from naturals to naturals, and it satisfies the following condition. So the condition is f of n plus 1 greater than f of n, and you have this true for all n belongings to naturals. Okay, so think about how you'll do this problem for some moment, and then you can start watching the video again to see its solution. So what we can do is, I hope you must have tried the problem, and so let's begin with the solution. So we can start, and let's make a claim that since the function is in naturals, so we can say that f of everything would be unique, because you have this inequality sign, and every f of n must have a unique value, and you see that you have a value f of 1 that must be minimal, like minimal from all of the other values. So what you can do is that you find the value of f of 1 and then try to strong induct on the other values. So maybe you could see if I write that. Okay, so let me start, and we can make a claim. So our claim is that since the function is in naturals, so we can have, actually we will have, so we will have unique values values to f of n, where n is a natural number. And then what we can do is f of 1 must have some unique minimal value. Now let's take a number, let's take a natural number k, for example, and then we'll solve using that. So we have f of k plus 1 greater than f of k, as k follows this property. So we wrote that from here, and then what we can do is, okay, let me see that. Does it work? Okay, so what we can do is, now let's take f of k plus 2 and then see what happens of f of k plus 1, f of k plus 1. So from this we can write this thing, that is f of k plus 2 greater than f of k plus 1. Let me rewrite this. Okay, so now what we can do is try to minimize this thing. So if we somehow make this value of k as equals to 0, so we can minimize the value of f of 1, as this whole thing would become f of 1 and this would be f of 1. So let's actually try to do that. So we have, now what we can do is, our goal is to do this thing. So our goal is somehow make f of k plus 1 equals to f of 1, or like if we try to make f of k plus 1 equals to 1, and then we can say k is the least value, so we can have f of 1. So our goal should be to make this as 1, and hence eventually we would get this as f of 1. This might sound vague, but bear with me and we'll see how we can do it using this. Okay, so now let's begin. This is the least value of f of 1 that f of n can take anyways, so it would be true for f of 1. So what I mean to say is that if f of n has a least value, suppose for example f of 1 has the least value, so f of 2 must have the second least value. So you must be able to understand this thing. So from here we can make this thing, that is f of 1 less than f of 2 less than f of 3, and that goes on till f of k. And k was our assumption, an arbitrary number that follows this, and that follows this property. So from here we see we can make another claim, that is Okay, give me some moment. You'll need to wait for 10 more seconds to actually sync my screen so that I can write on the whiteboard. It's actually syncing now, so it will take some time. I hope it gets done sooner so that I can start solving the problem. So there's a strict inequality between this thing, that is f of 1 less than f of 2 less than f of 3, since all of them have a unique value associated with them. Okay, let me see if I can write now. So it's taking time. I think you can think about this problem for some more time and then we'll restart again. So here's our proof. So think about this problem for some minutes and then we'll solve again. Okay, so now I can write on the screen and let's begin again. So this thing, we were here. Yeah, it works now perfectly. So let's start again. So we'll try to make a claim that is this thing, f of n equals to n, and then we will try to prove this using strong induction. So our goal should be clear to us so that we can proceed in the right direction. So we take another number that is n prime and use this property that is f of k plus n prime plus 1 equals to f of n prime plus 1, and this would be the n plus 1th value. So we are actually trying to prove from here that we left here. So that was f of k plus 1 equals to 1, and now we are proceeding from there. So let's see, and then it satisfies this inequality that was f of k plus n prime plus 1 greater than f of n prime plus k. And now it will have the values f of k plus n prime. Just give me a moment. So what we can do now is this thing, that is f of k plus n prime will have the values 1, 2 till k as we have the, actually this would be n prime, sorry about that. So this has this values, and if f of k plus n prime is 1 of f of 1, f of 2, f of n prime minus 1, so what we can do, let's write it here. If f of k plus n prime has one of the values, okay, so if f of k plus n prime has one of the values from f of 1, f of 1, f of 2, f of n prime minus 1. So we are not taking n prime from now. Actually, we are trying to strong induct. So we are not taking the f of n prime. So what we can have is that, so k will have the values 1 minus n prime, 2 minus n prime, and that goes on till minus 1. So this should be clear. And if f of, and now we are making another thing, if f of k plus n prime plus 1, here it was this thing, here it was k plus n prime, and here it is k plus n prime plus 1. So what we will have, if it has the values 2, 3 and n prime, so we'll again have this thing, as we are looking from the we are looking from the n prime plus 1th value. So what we'll have is this thing, f of k plus n prime equals to n, and this was the n prime plus 1th value. Actually not this, but this was the n primed value, sorry. So f of n prime has to occupy the values uniquely. So this was our claim using the naturals, that was f of n prime has to occupy the values uniquely, and so f of k plus n prime, this thing must like be true. Oh, sorry about that. This thing must be true. And now what we can do is we can let k equals to be 0, and this would satisfy all our problems, as this must be a unique value, and hence we'll have this thing, that is f of k plus n prime plus 1 equals to f of n prime plus 1, and that would be the unique n prime plus 1th value, and this is equals to n prime plus 1. So this is unique value of n prime plus 1th value. So we tried to induct on n prime plus 1 using n prime minus 1 and n prime. So our goal was like we find the unique value of k plus 1's value, and we prove that f of n prime equals to n prime. So let me write that. That was, we find we found a unique value we found a unique value to every f of k, where k belong to naturals, and hence we therefore found f of n equals to n, that this satisfies the inequality. So this must be clear to you, and this was the whole proof. So I'll let you think about for some more time, and then we'll do one last problem. Actually, I'll give you it as a homework. So let me write that till you can think about this one. Okay, so I've written down a homework problem, that is this one. It is taken from the David M. Burton. So you can try this one, and it would actually help you understand the parametrization technique that we learned in our previous lecture. Okay, thank you everyone for seeing the lecture, and hope you learned something useful, and the lecture was helpful to you. Thank you.